So first, let me do what every lecturer should do, which is correct the things I said wrong yesterday. There were two things I said wrong. One, as Ram pointed out, was the geometric interpretation of the eccentric anomaly. The one I gave you was wrong. The correct one is on Wikipedia, but it's sufficiently complicated that it's probably not worth thinking about. So just ignore what I said about that. Second, I said yesterday that there was no complete convergent power series solution to the three-body problem. That's not correct. There is a solution due to Sundman, and unfortunately the convergence is so slow that it's of no practical use except as a matter of principle. Okay, so
even more interesting.
I wouldn't dream of correcting your lectures. Okay, so I'm going to talk about the use of Hamiltonian theory to do celestial mechanics. And as I introduced yesterday, I'm going to try to work with Delaunay elements. So just as a reminder, those are square root of G, mass of the central body times the semi-major axis, G, which is L, times the square root of 1 minus E squared, and H, which is G times the cosine of the inclination. And the conjugate coordinates for those are L, which is the mean anomaly, omega, which is the argument of periapsis, and capital omega, which is the longitude of the node, of the ascending node. As I said, the real use of these is in the case where you don't have a pure Kepler orbit, but a Kepler orbit that's perturbed by some extra potential. The potential is just an energy, and so it can be written as a Hamiltonian. And so you're interested in studying the behavior of a Hamiltonian, which is the Kepler part. And again, from yesterday, that's gm squared over 2l squared plus some perturbation, which is believed, which we're going to take to be small. And since we're working in Delaunay coordinates, this is a function of the 6 variables, L, omega, and the time. And as I said, this nominally is making things more complicated because I've gone from a potential that's a function of 3 coordinates to a potential that's a function of 6 coordinates plus the time. But the advantage is that the Kepler Hamiltonian is so much simpler that in the end, you're better off working in the Delaunay coordinates. So the first question is, what general properties are there for the perturbing Hamiltonian, and is there any way we can simplify it? The first obvious simplification is because these are angle variables that go between 0 and 2 pi. That means that the perturbing Hamiltonian can't depend on these variables except modulo 2 pi, and that means you can always expand it in a Fourier series. And so the first step is that you can write this as a sum over 3 integers, j, k, and m, of some function of the actions, j, k, and m, of L, G, H, and maybe the time, times e to the I, jl, plus k, little omega, plus m, capital omega, minus some function of the time, j, k, m of time. Because the mean anomaly and the argument of periapsis are poorly defined in cases of circular or either zero eccentricity or zero inclination orbits, we will also sometimes use the mean longitude, lambda, which is L plus omega, and the longitude of periapsis, which is little omega plus capital omega. And so in those variables, the argument of the exponential would be j times lambda plus k minus j times the longitude of periapsis plus m minus k times omega minus the function of time. Okay, so the next simplification is to recognize that if the orbit's circular, all of these variables are defined, but not the longitude of periapsis, because there is no periapsis. But if this Hamiltonian is to make sense as a physical quantity that depends on coordinates, in that case it can't depend on omega. And so the conclusion is that if the eccentricity is 0, then H1, HJKM has to be 0 unless J equals K. Similarly, if the inclination is 0, the longitude of the node is undefined. And so if the inclination is 0, H JKM equals 0 unless M equals K. And these are important constraints, particularly because in most planetary systems you're dealing with orbits that have low inclination and low eccentricity. These two statements can be generalized, and the generalization is to say that the absolute value of H JKM goes like the eccentricity to the absolute value of J minus K. So that's consistent with that, but tells you how it varies if J is not equal to K, and it's also proportional to the inclination to the absolute value of K minus M. That's giving you the expression in terms of eccentricity and inclination rather than the Delaunay elements, but you can see from those expressions that L minus G is, for small eccentricity, E squared over 2 times L, and G minus H is I squared over 2 times G. And so these two expressions can simply be rewritten as absolute value of L minus G to the absolute value of J minus K over 2, and this would be absolute value of G minus H, the absolute value of K minus M over 2. And these, this particular property, for some reason, is called the Dalembert characteristic. And this behavior isn't mysterious at all if you recall that for small eccentricity and small inclination, you can think of eccentricity and argument of and longitude of the node as being polar coordinates, and it doesn't really make sense to do an expansion of a smooth function in polar coordinates when you're close to the origin. And so, for example, if I had some arbitrary smooth function of x and y in Cartesian coordinates, and I expanded it in polar coordinates near the origin, it would have an expression like f0 plus f1 or e to the I phi plus f2 r squared e to the 2 I phi. And the fact that the 2 up here is associated with the square of the radius is exactly the same as the Dalembert characteristic.
Can you say again what is that undefined in both cases?
when the eccentricity is 0, the direction of the apse is undefined. And if the inclination is 0, the direction of the node is undefined. And since they're undefined, they can't enter this exponent, and so the integer in front of them has to be 0. Okay. Let me leave that open. Another useful distinction between the terms in the disturbing function is to look at the case where the perturbing potential is 0. Where H1 is independent of time. And then H1 is the sum JKM H JKM L G H times e to the I JL plus K omega plus m times omega. And in this case, there's an obvious distinction between two kinds of terms. If J is 0, because omega and the longitude of the node don't change in the Kepler orbit, if J is 0, the argument of the exponent is changing very slowly, only as a result of the perturbations. So if J is 0, the argument of the exponent changes slowly. And if J is not equal to 0, the argument goes through a period, goes through 2 pi in a time which is the orbital period. Typically, the terms with J not equal to 0 are bigger. That is, their H is bigger than the terms with J equals 0. But because they're oscillating back and forth, whereas these are changing very slowly, the overall effect of these terms is often very much bigger. So these and these have come to be called the secular terms, and these are typically called the short period terms. And in general, much or most of the long-term evolution of exoplanet systems is driven by the secular terms rather than the short period terms. Okay. And finally, if you look at the case where the driving force, the driving potential, has a single frequency, then H1 is the sum JKM H JKM of L G and H times e to the I JL plus K omega plus M capital Omega minus, let me call it nu T, where this is the driving frequency. So for example, if the perturbation is due to another planet, nu would be some integer multiple of the orbital frequency of that planet. In this case, the distinction between secular and short period terms doesn't really matter, because even if J is 0 in this term in the argument is varying slowly. This frequency is varying rapidly, so the perturbation is varying rapidly. However, you can get an exceptionally strong effect when this term and that one cancel, and that would be when J times the mean motion is approximately equal to the driving frequency. And this, of course, is an example of a resonant term. And in some ways, resonant terms are like secular terms in that even a term with a small factor in front can have an unusually large effect. The difference is that the secular term can have a large effect over all of phase space, because when this term is 0, these two arguments don't change at all in the unperturbed system. Here, the effective resonance is limited to a rather small range in semi-major axis or mean motion, where the resonance condition is approximately satisfied. Yes?
Can you allow Jn to include some integer number times Jn?
Well, if you allow Jn to equal some integer times the frequency, the argument will still vary. But typically, if you've got, for example, if this represents the frequency of orbiting a second orbiting planet, the Fourier transform of the potential from the planet will have the frequency of the planet times various integers. I'll talk a little more about this later on, and it should become clearer. Okay, so with those preliminaries, I'd like to move to a couple of describing some specific examples. And the examples I'd like to do are orbits of satellites around an oblate planet, Kozai oscillations or Kozai-Lidov oscillations, resonances, and if there's time, maybe co-orbital satellites. So let me start with an ordinary satellite. The prototype to have in mind is, say, a low Earth communications satellite orbiting around, a low orbit communications satellite orbiting around the Earth. And the main perturbation there is the fact that the Earth is not spherically symmetric. So the gravitational potential from the Earth, or say from some planet, is minus g times the mass of the planet over the radius. And if the planet's axisymmetric, and it can be expanded in terms of multiples, Jn Rp to the n over r to the n Pn cos theta. So Rp is the planet radius. Jn is the nth multipole moment. And Pn is a Legendre polynomial. And of course, cos theta is the usual polar coordinate relative to the polar axis of the planet. You'll notice I've started from n equals 2 rather than n equals 1. The reason for that is that in contrast to electrostatics, in a gravitational field, if you've chosen your origin to be at the center of mass of the massive body, the first order multipole moment always vanishes. Moreover, in the case of the Earth, in the case of most planets, J2 is typically much bigger than all of the other ones. If the planet's has reflection symmetry around its equator, J3 and J5 and J7 are all 0. So by far the largest component is typically J2, and for the sake of simplicity, I'll just ignore the other ones. And then since P2 of x is 1/2 3x squared minus 1, and since this term is the unperturbed Kepler Hamiltonian, I can write the perturbing Hamiltonian as just g times the mass of the planet times J2 radius of the planet squared over 2r cubed 3 cos squared theta minus 1. Now, as I said before, there are secular terms and there are short period terms. The short period terms are important if you want to know exactly where the satellite is, but if you want to understand the long-term behavior of the satellite orbit, you may as well just look at the secular terms. Because the secular terms are the ones that survive when you average over one orbital period, they're the ones with j equals 0, I can figure out what the secular terms is simply by taking the Hamiltonian and averaging it over one unperturbed or Kepler orbit. Okay, so if I want to do this, there are two terms. This term has a 1 over r cubed, and if I want to average 1 over r cubed over the orbit, this is just 1 over the period integral 0 to the period dt over r cubed. And remember that the angular momentum is r squared times the rate of change of the true anomaly, and so I can replace this as 1 over p times L integral 0 to 2 pi of df over r. The period is 2 pi square root of the cube of the semi-major axis over g times the mass of the planet. The angular momentum is the square root of g times the mass of the planet times the semi-major axis, 1 minus e squared, and the radius is the usual expression for a Kepler orbit, a 1 minus e squared over 1 plus e cosine of the true anomaly. So you can see that when you substitute this for 1 over r, you'll get an integral df 1 plus e cos f. The cos f averages to 0, and so the integral is just 2 pi. And that says that when you plug all these things in and cancel them out, this integral is just 1 over a cubed 1 minus e squared to the 3 halves. The second component of the averaging is the cos squared theta divided by r cubed. And for that, you have to look at the geometry of the orbit a little. If this is a standard coordinate system, the reference plane, the xy plane, is the equator of the planet. There's the longitude of the node. Here's the orbit. This is the inclination. And the position in the orbit is the sum of the argument of periapsis plus the true anomaly. And so the distance the orbit has up in this direction is the sine of this times the radius. The component along the z-axis is that value times the sine of the inclination. And so it's pretty easy to see that the cosine of theta in terms of the orbital elements is the sine of the inclination times the sine of omega plus the true anomaly. And that means that the second average that you need in addition to this one, which is cos squared theta over r cubed, is just the same as this one with the addition of the cos squared theta. So it's 1 over PL integral 0 to 2 pi df over r times sine squared of the inclination sine squared of omega plus f. Once again, you can take the radius and put it in. It'll give you a 1 plus e cos f in the numerator. And when you expand out the sign, all of the integrals are easy. The answer turns out to be sine squared I over 2a cubed 1 minus e squared to the 3/2. So we have the two averages that we need. Yes?
So are we assuming anything about the orientation of the planet with that identity right there?
I'm assuming that the equator plane of the planet coincides with the xy plane. Okay, so with those two results, the perturbing Hamiltonian, I'm going to replace it with the secular Hamiltonian. So again, I'm neglecting the short period terms. It's just G, MP, J2, radius of the planet squared, over 4a cubed, 1 minus e squared to the 3/2 times 3 sine squared of the inclination minus 2. So we've got the secular Hamiltonian in terms of the orbital elements. It's not in terms of the Delaunay elements yet, but making that conversion is easy because these are the expressions for the Delaunay elements in terms of eccentricity and semi-major axis. And it's easy to convert this, and you get that the secular Hamiltonian is G times the mass of the planet to the 4th J2 radius of the planet squared over 4 L cubed G cubed 1 minus 3h squared over G squared. And of course, it's completely obvious when G is referring to the gravitational constant and when it's referring to the Delaunay element, because the gravitational constant always appears together with an MP. So that's it. This is a complete description of what happens to a satellite as it's going around the Earth, at least to order where you're only including the quadrupole moment and where you're neglecting the short period terms. So what do you conclude from this? It actually has a remarkable level of richness. The first conclusion is from Hamilton's equations. The rate of change of the variable L is, of course, minus the gradient of this with respect to the mean longitude, and that's 0. This is not a surprise. Remember that the secular approximation involves averaging, involves dropping all the terms that depend on the mean longitude. So this is kind of a tautology. This always happens in secular theory, but it does contain some interesting physics because L depends on the semi-major axis, and this tells you that secular terms can cause big changes in the eccentricity, big changes in the angle, but they leave the semi-major axes almost invariant. And one of the signs of that, even in the solar system, is that the variations in the eccentricities and the other elements of the planetary orbits are much bigger than the variations in the semi-major axes, because those are only due to the short period terms. The second conclusion, you look at Hamilton's equation for G is minus dH d omega. That's also 0 because the argument of periapsis doesn't appear in here. This is a much less trivial and less obvious fact. It's very important because since the semi-major axis is fixed, any variation in G is a variation in the eccentricity. Any variation in the eccentricity is a variation in the perigee distance. And if you've got a satellite that's orbiting at, like, say, the space station at about 300 kilometers compared to the Earth radius of 6,000 kilometers, and the eccentricity were to vary by 5%, the space station wouldn't last very long. So it's extremely important that the secular variations are independent of omega. That actually turns out to be a coincidence, which is only generally true for the quadrupole potential and not for other potentials. So it's just good fortune, so to speak, that the math works out so that we can have low Earth satellites survive. The other obvious conclusion is that since this doesn't depend on the node, dH by dt is 0. That's, again, trivial. H is the z component of the angular momentum, and you can't change the z component of the angular momentum in an axisymmetric potential. We can also go through the rates of change of the angles instead of the actions. And when you do that, not surprisingly, you find that the node of the satellite precesses d omega dt is the rate of change of h with respect to the Delaunay variable. It's minus 3 g times the mass of the planet to the 1/2 j2 planet radius squared over 2a to the 7/2 1 minus e squared cosine of the inclination. Nothing special about this. It says that the node goes retrograde, so the intersection of a satellite with the equator travels around the Earth backwards. Somewhat more interesting is omega, which is dH1 by dg. It's 3/4 g times the mass of the planet to the 1/2 j2 planet radius squared over a to the 7/2 1 minus e squared times 5 cos squared of the inclination minus 1. So here the apsis argument doesn't always precess forward. Whether it goes forward or backward depends on the inclination, and in particular there's a critical inclination given by the arc cosine of 1 over square root of 5, which is about 63 degrees, where omega dot is 0. This actually has applications. If you're an engineer who's designing satellite orbits, it can be useful to have a satellite where the omega is 0. In particular, we know that there are lots of communication satellites at geosynchronous orbit which keep them over a fixed spot in the equator because their orbital period is equal to the rotation period of the Earth. That actually doesn't work so well if you're trying to do communications in polar regions because the satellites are at the equator. And this is, in particular, is something that the Russians worried about quite a bit because they're at high latitudes. And so a lot of their communication satellites at least used to be designed, instead of being in geosynchronous orbits, to be at the critical inclination. That meant that the argument of periapsis was fixed, and so you could keep the argument of periapsis so the satellite was over Russia when it was at aphelion. It had high inclination so that it could reach even far northern parts of Russia, and because this can be a relatively low Earth orbit instead of a geosynchronous orbit, it costs less to put the satellite up. The cost instead is that because the satellite's going around, a single satellite isn't visible the whole time, and so you have to put up a fleet typically of 3 of them. So you're launching 3 satellites in relatively inexpensive orbits instead of 1 in a relatively expensive orbit. And again, if you weren't at the critical inclination, what would happen is the satellite would precess, so that instead of having good coverage for Russia, it would have good coverage for, say, South America. which they weren't particularly interested in providing. And I believe that the satellites for Sirius satellite radio use similar orbits. And the final thing I'd suggest is if you're not convinced that Hamiltonians are useful, just try deriving all of these results in Cartesian coordinates and see what happens. Okay, so this is basically a description of how you track the orbit of a small body due to an internal quadrupole moment arising from a planet. It doesn't have to be from the equatorial bulge of a planet. For example, if you had an object orbiting far outside a tight binary star, you would orbit average over the binary star, you'd get a J2, and exactly the same analysis would apply. So what I'd like to do next is look at the opposite case, where you have a quadrupole moment arising from a very distant object. In this case, the most natural thing to do is to assume that the distant object is an orbiting star. So for example, this would apply to a planet orbiting in a much larger binary star. So in this case, instead of, yes?
In order to assess the inaccuracy, I assume that the J4 will be the missing term.
Yes.
So this can give us also the time scale probably over which the accuracy of this is violated.
Yes, that's correct. So the J4, I think, is small.
How small it is?
Well, 300 times smaller or something. It's a lot smaller.
Yeah, a couple of orders of magnitude smaller, and in addition, there's an extra power of the radius of the planet to the radius of the satellite. So it really
For
is.
the Earth, it's non-hydrostatic at that level. So I'm
But
not
I think
sure
it's
what
still,
J2 is hydrostatic. But
Right.
J4 is beginning to be non-hydrostatic.
And the drag is not included here at all.
the drag is not included here. Right. See?
Do you have any insight that could explain this 53 degrees or this rate of 5, or even before that, the precession is into the opposite direction, except for, this comes out of this magic box?
Yeah, it comes out of the magic box. Okay. So now I'm going to look at what happens to a small body, a test particle, in a hierarchical binary system. So again, the natural application is a planet in a binary. In this case, the extra potential arises from the companion. So in a coordinate frame centered on the host star of the planet, the potential is minus g times the mass of the companion over square root r squared plus the radius of the companion squared minus 2 radius of the companion dotted into the radius of the planet. However, there's an additional term. This is the direct gravitational potential due to the companion star. However, we're working in the frame attached to the host star of the planet. And the host star of the planet is being accelerated by the companion star. So the frame that we're working in is accelerating at a rate which is g times the mass of the companion times the distance to the radius vector to the companion divided by the distance to the companion cubed. And as we know, this accelerated frame gives rise to an extra fictitious force which is minus the acceleration due to the frame. And if we want to express this as a potential, this has to be minus the gradient of some potential, which is fictitious. And if you look at this expression and this expression, it's clear that the extra potential has to be plus g times the mass of the companion r dotted into r of the companion over radius of the companion cubed. This is called the indirect term. And again, it's a fictitious term. It's an extra term which arises simply because we're working in the frame attached to the host star rather than the barycenter of the host star and the companion star. You have your choice. You can do things in either frame. Sometimes it's better to use one, sometimes better to use the other. Let me give you an example of when it's better not to use this frame. Suppose that you're looking at the opposite case to this, where you have a tight binary star that's going around, and you've got some really distant body going around them. If this body is much more distant than the difference between the positions of those two stars, roughly speaking, you'll see a single Kepler potential from the two stars. So if, say, the two stars are a year, and this is a comet with a period of 10 to the 6 years, the extra non-Kepler part of this will be quite small, and you'll happily be able to integrate this orbit with a time step of 10 to the 4 or so years. That's if you're working in the barycenter frame. If you work in the frame centered on one of the stars, you'll add the indirect term, and in the indirect term, the position of the companion is oscillating with a period of 1 year. And so you'll see an effect on the comet because it's sitting on one star, and so the comet orbit is jiggling back and forth in the frame centered on the star in a period of 1 year. And so if you pick the wrong frame, your integration time step will drop from 10 to the 5 years or 10 to the 4 years to a tenth of a year. So that's really not a good thing. So in a case like this, you want to be careful not to work in this frame. Of course, I speak from experience, so don't make the same mistake I did. Okay, now that we've got the indirect term, I'll erase this. Because we're looking at a hierarchical system in which the distance to the companion is much larger, I can expand things in terms of the ratio of r, the radius of the companion. I'll write this as minus GMC over RC square root 1 plus r squared over radius of the companion squared minus 2 RC dot r over RC squared plus the indirect term I then simply expand this in a Taylor series. You can see that the first term is going, because this is of order the small parameter squared, and this is of order the small parameter, the first term is going to be a minus GMC RC dot R over RC cubed, which exactly cancels the indirect term. So the remaining term is going to be second order in this small parameter and gives you an expression GMC, mass of the companion, over the distance to the companion cubed times 1/2 r squared minus 3/2 r dotted into the distance to the companion squared over distance to the companion squared. And that's the external quadrupole approximation. So it's the exact analog to the expression for the potential that I wrote earlier from the equatorial bulge, except it's arising from an external quadrupole instead of an internal quadrupole. Now we have to go through the same process that we went through for the satellite. That is, we have to average, except this time we have to average over both the orbit of the companion and the orbit of the planet. The expectation of 1 over the cube of the distance to the companion, we know already because we did that for the internal quadrupole. And that's just 1 over semi-major axis of the companion cubed, 1 minus the eccentricity squared of the companion to the 3/2. Using the same techniques, we also need expectation of the square of the cosine of the true anomaly over the companion cubed. We need the same thing for the square of the sine over the companion cubed. These turn out to be the same, and they're just a half of this one. Those are all the terms you need to average over the orbit of the companion. And once I do that, the expression for the Hamiltonian becomes g, mass of the companion, over 4 times the semi-major axis of the companion cubed, 1 minus the eccentricity squared to the 3/2, and then twice expectation of r squared minus 3 expectation of x squared minus 3 expectation of y squared. These are now averages over the planet, and I've gone to a particular coordinate system in which the companion orbit in the xy plane and its periapsis is along the x direction. And then all you need is to evaluate these 3 averages. Yes, and this is the secular Hamiltonian again. The techniques you use to get the averages for the outer planet, you can also use to average over the inner orbit. That is, by converting integral of time over to integral of the true anomaly. But it turns out that when you've got positive powers instead of negative powers, there's a slightly better way to do it, which is to work with the eccentric anomaly. So the expectation of r squared is 1 over 2 pi integral over time, or integral over the mean anomaly of r, and in terms of the eccentric anomaly, this is 1 minus e cos u squared. But we know that Kepler's equation says L is equal to u minus e sine u, and so dl is 1 minus e cos u, and so this average is just 1 over 2 pi integral a squared over 2 pi du 1 minus e cos u cubed. And if you don't like the eccentric anomaly, try doing the average with the mean anomaly and see, with the true anomaly, and see which is easier. And this is just a squared 1 plus 3e squared over 2. Yes, thank you. You also need expectation of r squared cos squared f. This is a squared 1/2 plus 2e squared. You need expectation of r squared sine squared f, and it's a squared 1/2 minus 1/2 e squared. Okay, so with those averages done, you can simply write down what the secular Hamiltonian is for the external quadrupole. So the secular Hamiltonian is g times the mass of the companion over 8 semi-major axis of the companion cubed, 1 minus eccentricity squared to the 3/2, semi-major axis squared times 1 minus 6 times the square of the eccentricity minus 3, 1 minus e squared cos squared of the inclination plus 15 e squared sine squared I sine squared omega. Now, I can convert this into Delaunay elements, but you can all do it, but it doesn't buy us a whole lot. So I'm not going to bother to do it. I'll leave in these elements. But if you think in terms of Delaunay elements, the result's independent of the mean anomaly. Again, that's just the secular, that's a result of the averaging approximation. It says that in this approximation, the semi-major axis of the planet is constant. It's independent of the node. It's independent of capital omega. And that says that since capital omega is conjugate to the Delaunay variable h, which is the z component of the angular momentum, that's conserved. And so h, which is square root GMA square root 1 minus e squared cos I is conserved. And again, as in the case of the internal quadrupole, where the Hamiltonian was independent of little omega, which was an accident, in the case of the external quadrupole, it turns out that the Hamiltonian is independent of capital omega. And that wasn't obvious because we allowed the companion to have an eccentricity, so there's a difference between being pointed along the line of apsides of the external companion or perpendicular, but it happens that the dependence on omega cancels out. So what's the implication? Is there a way to understand the implications of this? Let's suppose that here's the host star, here's the companion going around on an orbit that's perpendicular to the plane of the blackboard, and that the planet's initially in a circular orbit inclined to the orbit of the external star by some inclination I. Well, and let's suppose that the orbit's initially circular. Well, we know that h is conserved, and let's say that the initial inclination is I0. Well, since h is conserved, initially this is 1 and that's I0. So however the orbit evolves, it has to evolve so that 1 minus e squared cos I is cosine of I0. Moreover, however it evolves, it has to conserve the energy, so it has to conserve this Hamiltonian, which is independent of time. And so that says that the quantity in square brackets, which is 1 minus, first two terms are 1 minus 6e squared. This term is obviously just minus 3 cos squared I, cos squared I0, plus 15 e squared. Then sine squared I is 1 minus cos squared I, so it's 1 minus cos squared I0 over 1 minus e squared times sine squared omega. Has to be a constant. Well, what constant is it? Well, initially the eccentricity was 0 and I was I0. So that's 0, that's the same, and this is 0. So it has to be 1 minus 3 cos squared I0. And cos squared, this and this cancel. They're on the left and right hand side, that and that cancel. And so the conclusion is that conservation of the Hamiltonian tells you that 2e squared 1 minus e squared is 5 e squared sine squared omega sine squared I0 minus e squared. Well, that's got two solutions. either E equals 0, that's an obvious solution because that's what we started with, or sine squared omega is 2/5 E squared minus 1, E squared minus sine squared I0. It's not completely obvious what that equation is telling you, but if you just plot E squared can only go between 0 and 1, sine squared omega can only go between 0 and 1. But when E is 0, this is 2 over 5 sine squared I0. The curve goes up like this, goes through a singularity at sine squared I0, and then goes back down and ends up at 0 when E squared is 1. So if you think about this for a second, since sine squared omega has to be between 0 and 1, if sine squared omega, sine squared I0 is less, if sine I0 is less than the square root of 2/5, there's no solution. So the only solution is E equals 0. What that tells you is that when the initial inclination is less than this, which is 39 degrees, the planet stays in a circular orbit. If the inclination is bigger than this, there are other solutions, and the planet has the opportunity to oscillate in eccentricity. And these oscillations, well, I call these oscillations Lidov Kozai oscillations. What actually happens to the argument of periapsis, to the eccentricity and the inclination during these oscillations, you can get simply by plotting the level contours of the Hamiltonian. And let me just go to the slides for a second to show you the, yes. If you have a non-axisymmetric mass distribution interior to the orbit, you can expand its potential in multiple moments. And the dominant term will be the quadrupole. If you have a non-axisymmetric mass distribution outside the orbit and a long way away, you can expand the potential in multiple moments, and it will also be a quadrupole. The difference between the two of them is basically, you probably remember from electrostatics, is that the expansion of, say, 1 over r minus r prime is some sum of the smaller of them to the L over the bigger of them to the L plus 1 times YLM theta phi YLM star theta prime phi prime. So in one case, if the mass distribution is an external quadrupole, it's the bigger. If it's an internal and it's the bigger, and the particle you're interested in is the smaller. If it's an internal quadrupole, the particle you're interested in is the bigger radius. Okay, could we turn on the projector? Yes.
You know why Kozai and Lidov's original papers were so confusing?
Yes, let me say a little bit about that.
This is more simple.
So this is an example of a planet with an initial inclination of 60 degrees. This is zero eccentricity, eccentricity of unity. This is the argument of periapsis. And you can see that the orbits at zero eccentricity are actually unstable. That is, at this inclination, they can't stay circular, and they slowly work their way up to very high eccentricity and work their way back down again. And that cycle repeats on the secular time scale, that is on a time scale which is proportional to the strength of the external perturbation. So let me say a little bit about the history. First of all, for many years these were called Kozai oscillations, but the history is actually that Lidov was working, he was part of the design team for the trajectory of the first Soviet spacecraft to go to the far side of the moon. So those of you who are at least as old as I am will remember that up until the early 1960s, nobody had ever seen the far side of the moon, and in an impressive technical feat, the Soviet Union sent a spacecraft which took some really lousy pictures of the backside of the moon, but did return them successfully. The orbit of the spacecraft was, first of all, it was a high inclination orbit because it was launched from Russia. It was a highly eccentric orbit, so it went behind the moon and came back and then transmitted all the data back when it was close to the Earth at perigee again. After the successful picture taking, which took place in something like October, the satellite eventually crashed back into the Earth sometime the following spring. And although I don't know, what I believe happened is that that Lidov became interested in the why the spacecraft had behaved in this strange way, and then wrote a paper on Kozai-Lidov oscillations. I don't think his original paper was confusing. I thought it was it may have been, it's confusing if you try to read it in Russian, but at least for me. But there are English translations on the web, and I actually thought it was an exceptionally clear paper. He presented the paper at a conference in Moscow. Kozai was at the conference, and Kozai had the idea of applying this technique to asteroids. Instead, came back to the US, wrote a paper a little later, which appeared in an astronomical journal, in which he acknowledged Lidov. But I think because communications between the West and the East weren't so good back then, and because Lidov's papers were Lidov's initial papers were in Russian, Kozai ended up getting most of the credit. But so the name has is switching gradually from Kozai oscillations to Kozai-Lidov oscillations. I think it should be, well, actually, I think it should be Lidov. But anyway, I'm trying to move one step at a time and calling it Kozai-Lidov. There are a couple of remarkable things about this discovery. First of all, there's nothing that I've done here that Laplace didn't know about, right? So Laplace could easily have derived all this stuff. The second remarkable thing is that even after Lidov and Kozai derived it, there was a latency period of about 20 years. These are citations from ADS. So the papers were back here, and you can see that in both cases they got essentially no citations for something like 30 years. And since then the citations have been rising exponentially. We'll see how long the exponential continues. But clearly, even though it was a very interesting phenomenon, obviously nobody paid attention to it for 30 years. And I think it was only really once the exoplanet community started to pay attention that people started thinking about these papers. There are many examples of applications of these, but let me make a couple of other points about the oscillations themselves. In this case, the maximum eccentricity is about 0.8. This is a function of the initial inclination. In particular, in the limiting case where the inclination approaches 90 degrees, the maximum inclination is 1, and you can get collisions between the planet and the star. Second, as I said, the trajectory that the planet follows doesn't depend on the mass of the companion or the distance to the companion. Those only affect the time scale. So no matter how far away the companion is, or no matter how small it is, in principle it can induce huge oscillations in the eccentricity of the planet. Obviously, in the limiting case, something has to go wrong. What goes wrong is that either the timescale for the oscillation can be longer than the age of the star, or there can be some other source of precession that dominates over the effect of the quadrupole, and that will quench the oscillation. That could be a second planet in the system. In a single planet system, it usually turns out to be general relativity. So remarkably, I think you really can't understand exoplanets without including general relativity. There are many other applications outside exoplanets, but my favorite one actually is also due to Lidov. He pointed out that if you just take the moon, it's an artificial example, but what have I done? 1 second. It's an artificial example, but suppose that you take the moon, leave all its orbital elements the same, and simply rotate the moon's inclination to the ecliptic to 90 degrees. That's what the orbit looks like. So the blue is the current lunar orbit. Earth-Moon distance undergoes small oscillations due to the eccentricity of the moon, which continue indefinitely. If you rotate the moon to 90 degrees, then within 4 years it'll crash into the Earth. Very hypothetical, but a very dramatic example of what Lidov-Kozai oscillations can do for you. They have many possible applications to exoplanets. I'll just mention one. An extremely optimistic and probably unrealistic view is that many stars have binary companions, and maybe all of the eccentricities of the giant planets that you see in radial velocity surveys arise from Kozai-Lidov oscillations induced by the companions. That actually doesn't work so well. This is a plot of orbital period against eccentricity with the planets that are members of binary star systems in red. And you can see that there's no obvious correlation between the eccentricity and the presence of a binary companion, except you'll notice that out of the top 10 highest eccentricities, more than half of them are in binary systems. The binary systems are grossly overrepresented up here. And so it's at least possible, there's suggestive evidence that when you go up to the very highest eccentricity systems, you are seeing Kozai-Lidov oscillations. Okay, yes?
I think that we are missing many companions, many star companions.
I
Especially if you consider the secondary low mass against stars, the Jupiter and Gaia will come up.
I agree.
And also about the numbering, I would say that out of the 8, out of the 7 top 5 are indirect.
Well, there's one behind the label here, so there's 1, 2, 3, 4, 5, 6 in binaries. I agree. On the other hand, you would still expect, even if we're missing a lot, you would still expect to see the fraction of binaries going up steadily through here, not just in the top 20%. Also, as I said, having an extra planet in the system suppresses the oscillations, and although the eccentricities planets in multi-planet systems are somewhat smaller, they're still substantial. So I don't think these are can be the whole story. Yes?
Yeah, maybe it's the web of the same plot, because it's a bit hard to judge how many we actually compare the two.
No, but it takes 30 seconds to generate these plots on exoplanets, so I suggest you just go ahead and try it.
Okay, oh yeah.
Other questions?
I have a question on the interpretation of the inequality on the sign, the inclination. Like, because you do the calculation and at some points the equality is only possible for a range of values of the equation. But what does it mean really? So we can say that it is unstable, but what is the reasoning that says that if the inequality does not hold, then the object is unstable?
Right. So you're correct to recognize that as a gap in the reasoning. I was only giving that equality as the simplest way you could see why that critical angle of 40 degrees arose. The correct way to do it is to plot the contours of the level surfaces of the Hamiltonian. Which shows that, well, so if you plot them this way, what you find is that this is a separatrix, and zero eccentricity orbits come along here and reach a neutral point of the separatrix and come up here. What this really tells you, once again, is that eccentricity and argument of periapsis are not good variables to use. You may remember that we introduced a set of Poincaré variables, which are more like Cartesian coordinates. If you rewrite the same Hamiltonian in Poincaré elements, what you will find is that at the critical angle, the solution at zero eccentricity is still a solution, but becomes an unstable solution. And so if you start a point epsilon away from zero eccentricity, it will start to engage in the oscillation going up to high eccentricity. It's just all much clearer if you use Poincaré elements.
So it's just due to the coordinates?
These are not, these coordinates don't make it obvious what's happening, I agree. But if you do it in Poincaré coordinates, it's just a change of the neutral point from a stable neutral point to an unstable one. Mm-hmm.
If I replace the external star by an external disk or external ring, the Lidov Kozai operation still happens?
Yes, because all that matters is the quadrupole moment. As long as any quadrupole external quadrupole moment will have the same effect.
Even if it's axisymmetric?
Yes, because again, in this quadrupole approximation, the dependence on the argument of the node went away, and so it's an axisymmetric potential anyway.
So what happens if you throw away the indirect stone equivalent?
Well, why would you want to do that?
Well, which is how the back indirect play a role?
Well, throwing away the indirect term is equivalent to taking a hammer and nailing one of the stars down into a piece of wood so that it can't move. If you wanted to do that, you would indeed get very different behavior, but it's not worth spending a lot of time
For
on.
example, if you have an external ring, like we talked about, and indirect and just
But then there would also be no first order term in the direct term, and so you would still only get a quadrupole. Okay, that's all for the slides. Thank you. Okay, you'll be getting more on Lidov oscillations, I think from some of the other speakers next week. The third example I wanted to talk about is resonances. And I'm not sure I'll get through with them, but if I don't, we'll just stop at 3:30, and since I have a couple more lectures, I'll just intrude onto one of the other lectures. So in this case, I'd like to look at the case of two planets in a single system and to ask what the second planet does to the first one. In order to keep things as definite as possible, I'll look at the case where there's an outer planet on a circular orbit. So it has a mass MP and a semi-major axis AP and zero eccentricity. And then we'll assume that the inner planet has negligible mass and is the inner planet. Its mass goes to 0. Semi-major axis is A. I'm going to assume that its inclination is 0. That is, everything's coplanar. None of these assumptions are critical. The analysis can be generalized to include small inclinations, small eccentricities in both of them, but I'm trying to give you an example which is as simple as possible. Again, I'm going to work in a reference frame that's attached to the star. And so the Hamiltonian, the perturbing Hamiltonian, is minus g times the mass of the exterior planet, the square root of AP squared plus r squared minus 2r AP cos phi minus phi p. I'm using A for the semi-major axis of the outer one because I've assumed that its eccentricity is 0. I'm not assuming that the eccentricity of the inner planet is 0. And then I have to add the indirect term, which is g mp r over AP squared times the cos phi minus phi p. Because the outer planet is circular, phi p, I can just say set to be npt, where np is the mean motion, square root g times the mass of the central star over AP cubed. In the case of Lidov-Kozai oscillations, we were assuming that the outer perturber was a long way away, so you could expand this in a Taylor series. In this case, I'm not going to assume that. The planets can be reasonably close together. But because I'm going to assume the orbits don't cross, so AP is bigger than R, that means I can take this out of the square root, GMP over AP square root 1 plus R squared over AP squared minus 2R over AP cos of phi minus NPT plus GMP R over AP cos phi minus NPT. Thank you. Okay. The Hamiltonian has to be periodic in phi, so I can expand it in a Fourier series, including both the direct and indirect terms. I can always write this as GMP over AP times the sum from m equals 0 to infinity of some coefficient am that only depends on R over AP times the cosine of m phi minus npt. The next thing you have to do is to evaluate these coefficients. That's straightforward using Fourier analysis, but you do have to do an integral. All of this was first done by Laplace, and so I introduce the standard thing is to call these Laplace coefficients. They're integrals 2 over pi, integral 0 to pi d theta, cosine of m theta over square root 1 plus, not over square root, over 1 plus x squared minus 2x cos theta to the s power. Obviously, we're interested in the case where this is a half. There's a huge literature on these things, recurrence relations, relations to other special functions. I think they're a confluent hypergeometric function or something, but anyway, yes.
Should the R over AP be raised somehow?
Which one?
Expansion.
This? No, it's just a function of, that is apart from the common factor of AP, the only variable that appears in here is R over AP. And this is some periodic function of phi that also depends on R over AP. And so I can define these to be whatever I like. I'm sorry, that should be the... No, this is a function of, not a multiplication. Right, sorry. And the relation between the AMs and Laplace coefficients is that it's pretty simple. AM is a half B1 half 0 of x if n equals 0. It's B1 half 1 of x minus x if m equals 1. The extra x is just accounting for the indirect term. And B1 half m of x if m is greater than 1. Okay, at this point, I'm going to make one additional approximation. Since planets typically have relatively small eccentricities, I'm going to now try to expand the disturbing function, this potential. Oh, yes, sorry, I should say this. Once you get into planetary theory, this is usually called the disturbing function, except when the disturbing function, so the disturbing function is h1, except, or maybe sometimes it's minus h1. And again, I can't help it. That's what people do. Yes.
When m is equals 1, that means minus x comes from the indirect.
Yes, that's right.
Why does indirect term disappear in all other m's?
Because the indirect term is proportional to cos phi minus npt. So when you do an expansion like this, it only appears when m equals 1. Okay, so you have to allow me to assume that the eccentricity is much less than 1. And then if I'm going to replace r and phi by the orbital elements, you need an expansion of them for small eccentricity. This is pretty easy to do, and I'm not going to, well, for r, it's a 1 minus e cos u. We know that L is u minus e sine u. So to first order an eccentricity, you only need u, the relation between u and L, to 0 order. So it's just a 1 minus e cos L plus order e squared. Similarly, the true anomaly is L plus 2e sine L plus order e squared. So with that, you know what, you can expand, you can replace r by the orbital elements, and then phi is just f plus omega, and so that's the same as lambda plus 2e times the sine of lambda minus omega. Okay, so let me stop there, and I think my next lecture is supposed to be on numerical methods, but I'll just spend the first few minutes finishing off the discussion of resonances. Thank you.
Additional questions?
So to say eccentricity versus octal period is bigger does not show any correlation between eccentricity and the binary
Mhm.
size. So I'm just thinking because protoplanetary disk must once appears in the in the planetary system. If they could also force Lidov Kozai effect, would they ever, contribute enough eccentricity to those blue dots, which appears to have only one single star, but they still have significant eccentricity?
Well, I think it's my belief anyway is that it's difficult to induce these oscillations in a protoplanetary disk, because if it's a gas disk and you start to induce these oscillations, the orbits will intersect and the oscillations will get damped out pretty quickly.
Yeah, but we're thinking if the disk just disappears from the inner side, as what's already observed in many cases, then maybe the outer, it would be only an outer external disk. Is that correct?
Well, but then if you made planets in the inner disk and the inner disk disappeared, they'd likely be coplanar with the outer disk, and then you wouldn't introduce any oscillations.
Questions? Okay, so we have a break until the next talk. Thanks, Scott.
And the next talk is at 4?
Yes, 4 o'clock.